Strovay. Well, that's the way we say hello in Bulgaria. Hello, children. How are you people doing? I'm saurabhkumardutt, and I'm here to teach you people a little bit of mathematics. Now, children, this majestic place that you get to see is actually the Aqua Park in Nesebar, Bulgaria. It's Europe's largest water park. It has 10 million liters of water. It has been built by the highest security standards. It has 38 slides, the total length of which is 2,537 meters. Further, it also has the name of the slides to be pretty precarious, and you're going to be excited when you hear their names. Their names are Tornado, Tsunami, Black Hole, King Cobra. You've got to go in all of these slides and have fun. And I'm sure when you have fun once, you will obviously like to take those slides once again. But remember, there are many slides for you to complete in a single day. And for that matter, there are other places also to visit in this water park, like the Treasure Island, the House of Ice Creams. Then you have a fish spa, and also to choose from any of the 6 different restaurants and bars which serve you great food, mocktails and cocktails. But do remember, while having fun in Bulgaria, all the people of Bulgaria that you go and meet there, do say to them, Strovay. In this note, children, I'm going to start off this lecture where today we're going to discuss about continuity and differentiability. Now, we've already looked up continuity and we have also looked up what is differentiability. But remember here, we're going to talk about a theorem which is pretty important. That is, this tells us that if there is a function which is already differentiable, then it is also going to be continuous, right? So the theorem is this, that if there is a function which is already differentiable, then it also has to be continuous. So first I'm going to write the theorem for you people, and after that we will be discussing what this theorem is like. So when we talk about this theorem, the theorem goes like this. If f of x is a function which is differentiable at x is equal to a, then it will be continuous at x is equal to a. However, the converse is not true. That means if you talk about a function to be continuous and you expect it to be differentiable, that is not going to happen, right? So here, guys, by this theorem, we can say that if we have here, say, a function which is differentiable at x is equal to a, then we will have the left hand derivative to be equal to the right hand derivative. Or in other words, if we talk about limit h tends to 0 minus f of a plus h minus f of a, which is to be divided by h, that is the left hand derivative, will be equal to limit h tends to 0 plus f of a plus h minus f of a divided by h. That is, the left hand derivative is equal to the right hand derivative, as in the theorem you've been given that the function is differentiable at x is equal to a. So if you have this, then you expect that you will have the left hand limit to be equal to the right hand limit to be equal to value of the function at the point a. Or in other words, if we talk about limit h tends to 0 minus f of a plus h, right, that should be equal to limit h tends to 0 plus f of a plus h, right, and that will be equal to f of a, right? So this is what we will have. But if we talk about the converse of this theorem, that is, if there is a function which is already continuous, then we cannot expect that it is going to be differentiable. However, there are going to be cases where it can be differentiable, but for sure we cannot say that if there is a function which is continuous, it is also going to be differentiable. Now the other thing is that if you have a function which is not continuous, then for sure you can say that it is not going to be differentiable. As if it is to be differentiable, then it is also going to be continuous. As it is not continuous, so obviously it will also not be differentiable, right? So all of these things that I've told you people, I'm going to quickly repeat so that there is no ambiguity about what we've discussed. The theorem tells you this, that if there is a function which is differentiable at x is equal to a, then the function is also going to be continuous at the point x is equal to a for the domain of the function. Now, when by the theorem we say that it is differentiable, we will say that the left-hand derivative is equal to the right-hand derivative. Or in other words, we will say that limit h tends to 0 minus f of a plus h minus f of a divided by h is equal to limit h tends to 0 plus f of a plus h minus f of a divided by h. And then for sure we can say that at x is equal to a, the function is also continuous, or in other words, the left-hand limit is equal to the right-hand limit is equal to the value of the function at a. So we have the left-hand limit, which will be limit h tends to 0 minus f of a plus h is equal to limit h tends to 0 plus f of a plus h, which is equal to f of a. Right? So this is what we have. When we have a function to be differentiable, it is also going to be continuous. However, the converse is not going to be true. That is, if there is a function which is continuous, it is not for sure going to be differentiable. But we have another corollary, or there is another part which we can derive from this theorem. That is this, that if there is a function which is not continuous at a point x is equal to a, it is also not going to be differentiable. So guys, all of these facts that you've learned here is what is going to be used in sums now. So let's get ahead and do some sums. Discussing the next sum, which is something like this. Quickly look it up. I'm going to give you 10 seconds time, after which we're going to discuss this sum. Okay guys, now discussing the sum. Here in the question we've been given to show that f of x is equal to mod of x minus 2 proves that the converse of the theorem on the differentiability and continuity is not true at x is equal to 2. That means if we have the function to be continuous at x is equal to 2, right, it is not necessarily differentiable. So here what we do is, first we're going to talk about the continuity of the function, right? So we will say that for continuity of f of x at x is equal to 2, we will now have here the left-hand limit to be equal to the right-hand limit to be equal to the value of the function at 2. That is, limit x tends to 2 minus f of x should be equal to limit x tends to 2 plus f of x, which should be equal to f of 2, right? And thus, if you talk about limit h tends to 0 minus f of 2 plus h, this is how we can write x in terms of 2. That will be equal to limit h tends to 0 plus f of 2 plus h, right, is equal to f of 2. Now, further now, we keep the value of x to be 2 plus h, and we talk about the value of the function. Now, when we talk about the left-hand limit, we have limit h tends to 0 minus the function is x minus 2, or in other words, it's going to become equal to 2 plus h minus 2, and we talk about mod of this function, and that further is to be equal to limit h tends to 0 plus the function is mod of x minus 2, that means 2 plus h, and from that we've got to subtract 2, and we close this mod, and that should be equal to f of 2, which is mod of 2 minus 2. Right, in the next step now we solve this, we get 2 and 2 getting cancelled in the left hand limit as well as in the right hand limit, and further also in the value of the function at 2. So as such, the left hand limit now becomes equal to limit h tends to 0 minus mod of h, right, which is further to be equal to limit h tends to 0 plus mod of h, which is further equal to mod of 0, that is going to be 0. Right, now when you talk about keeping the value of h, which is infinitesimally small but negative, you got to remember here that we talk about the function f of x. If it is a mod of x, then this is equal to x if x is greater than or equal to 0, and this is equal to minus x if x is less than 0. So here, as we have the value of the function to be less than 0, then what we do is we can keep in its place minus h, so that whatever is negative will automatically become positive. Now when we talk about the right hand derivative, we will have here limit h tends to 0 plus, as h in itself is infinitesimally small but positive, so it will remain to be itself, and the right hand and the value of the function at 2 is already 0. Now when we next keep the value of h as it is infinitesimally small, we will keep it to be 0. As such, minus 0 doesn't make any sense, thus it becomes equal to 0. The right hand limit also becomes equal to 0, and the value of the function at 2 is also 0, right? So therefore we can now say that limit x tends to 2, f of x is continuous, as the left hand limit is equal to the right hand limit is equal to the value of the function at 2. Now further guys, we will now be talking about the differentiability at x is equal to 2. At x is equal to 2, for differentiability, we should now be having the left hand limit to be equal to the right hand limit. The left hand derivative should be equal to the right hand derivative. So left hand derivative is to be equal to the right hand derivative. And further we talk about this guys, we will now have limit h tends to 0 minus f of 2 plus h minus f of 2 divided by h is to be checked with limit h tends to 0 plus f of 2 plus h minus f of 2 to be divided by h. Now further guys, after this, next what we do is when we talk about the value of the function, when it is slightly less than 2, then the function is limit h tends to 0 minus the value of the function when it is slightly less than 2 is here the function to be the same, that is mod of x minus 2. So we have in place of x 2 plus h, right, from which 2 is to be subtracted, and we have a mod here, minus we have f of 2, which we've already found out to be 0, and this is to be divided by h. Now when we talk about the right hand derivative, it is limit h tends to 0 plus f of 2 plus h is again going to be the same function, that is 2 plus h, from which we're going to subtract 2, and from that we will be talking about subtracting f of 2, which is 0, and that is to be divided by h. So further guys, when we divide this by h, now we next have here plus 2 minus 2 getting cancelled in the left hand derivative as well as in the right hand derivative. So we now have a mod of h, which now is going to become equal to limit h tends to 0 minus h, as h in itself is negative, so when we multiply it with minus sign, it's going to become equal to positive, and when from that we subtract 0, it will remain to be minus h divided by h, where h will get cancelled and the left hand derivative will come to minus 1. Now when we talk about the right hand derivative, we have limit h tends to 0 plus 2 getting cancelled, mod of h will remain to be h because it is positive, from which when we subtract 0, it will remain to be h. When divided by h will get cancelled, as such the right hand derivative will become to be 1. Therefore we can say that if we talk about the left hand derivative, it is not equal to the right hand derivative, and therefore further we can say that limit x tending to 2 f of x is not differentiable, and it being not differentiable, it's been shown that when the function is continuous, it is not necessarily differentiable, right? And therefore you can say that therefore converse of theorem on continuity and differentiability is not true. Right? So guys, now I'll just quickly discuss this all over. In the question, you've been given here that you've got to show that the converse of the theorem on differentiability and continuity is not true at x is equal to 2 for the function f of x is equal to mod of x minus 2. Now here what we do is we first talk about the continuity of the function at x is equal to 2. That is, we talk about left hand limit to be equal to right hand limit to be equal to value of the function at 2. Now here we talk about that to be limit x tends to 2 minus f of x to be equal to limit x tends to 2 plus f of x to be equal to f of 2, right? Which is by the denomination of taking x to be 2. Then we bring in the infinitesimally small quantity that is h. So when we talk about limit h tends to 0 minus f of 2 plus h, that is further to be equal to limit h tends to 0 plus f of 2 plus h, which is further to be equal to f of 2. Right? Now here, when the value of h is infinitesimally small and negative added to 2, this point is going to move on the left hand side of 2, and thus we are talking about the value of the function at a point which is lesser than 2. So the function, whether it is less than 2 or greater than 2, the function remains to be the same, that is mod of x minus 2. So we will have it to be mod of 2 plus h in place of x minus 2, where 2 gets cancelled and we have mod of h. Now when we talk about the right hand limit, there too the same happens, that is, we have 2 plus h minus 2, where 2 gets cancelled and we have mod of h, right? And which further is to be equal to mod of 2 minus 2, right? So here further what will happen is we will have both the 2's getting cancelled and this will become mod of 0, that is 0. Now when we talk about the left hand limit, we have mod of h. Now here we've got to remember that when the function is equal to mod of x, that's equal to x if x is greater than equal to 0, and that's equal to minus x if x is less than 0. So as such, when we talk about the function mod of h where h is negative, it's going to become equal to minus h. And then further, when we keep the value of h to be infinitesimally small, that is 0, so it becomes equal to 0 because minus 0 doesn't make any sense, right? So further then, when we talk about the right hand limit, we have the value of h to be positive, as such it will remain to be h, right? But as h is infinitesimally small, when we keep its value to be 0, it further again becomes equal to 0, and for the value of the function at 2, we've already seen that it is 0, right? So as such, all of these three being equal, we have the left hand derivative to be equal to the right hand, the left hand limit to be equal to the right hand limit to be equal to the value of the function at 2, and thus limit x tends to 2 f of x is continuous. Next, now after this we talk about the differentiability of the function, because we are talking about the converse of the theorem to be true. As such, if it is continuous, it has to be shown that it is also differentiable. So further, when we talk about the left hand derivative and the right hand derivative, both of these have to be equal for it to be differentiable at x is equal to 2. Now for the left hand derivative, we talk about the limit h tends to 0 minus f of 2 plus h minus f of 2 upon h. Similarly, we talk about the same formula to be used when h is tending to 0 plus for the right hand derivative. We keep the value of the function, which is mod of x minus 2, that is, in place of x we substitute 2 plus h. 2 gets cancelled, we get mod of h. H being negative, it becomes equal to minus h, and from which f of 2, that is 0, is subtracted. As such, h getting cancelled, we get the left hand derivative to be minus 1. Now when we talk about the right hand derivative, we have f of 2 plus h, which again becomes equal to mod of x minus 2, that is mod of 2 plus h minus 2. So we get a mod of h. Now as h is positive, so mod of h will just become equal to h, from which f of 2, that is 0, is subtracted, so it remains to be h divided by h. Now h gets cancelled, as such we get the right hand derivative to be 1. So the left hand derivative is minus minus 1, the right hand derivative is 1. Both of these are not equal to each other. As such, you will say that limit x tends to 2f of x is not differentiable, and therefore the converse of the theorem on continuity and differentiability is not true, and thus it has been proved. So are you guys all clear about this? For sure. Brian? That's good, guys. Now after this, we'll be discussing the next sum, which goes something like this.